In their reactions with halogens, alkynes behave highly analogously to alkenes. They react with the elemental halogens to give products of anti-addition to the 2 carbons of the alkyne. If we use one equivalent, we get vicinal dihaloalkenes. You can see that here with 1 halogen added to each of the carbons of the alkyne. And if we use 2 equivalents or more of the halogen, we can end up with tetrahaloalkenes. Tetrahaloalkanes, in which we've got 4 new X atoms in the product, 2 X's linked to each of the carbons of the alkyne. And from studies of the stereochemistry of these alkene products, we know that the reaction is stereospecifically anti or stereoselective for the trans or E-alkene with X's on the opposite sides of the alkene product. However, a halonium-type ion is likely not involved in this first addition of X2. The mechanism here is most likely termomolecular, involving the halide anion and the halogen, the elemental halogen, with the halide anion adding as the electrophilic halogen atom adds at the same time. The details here are not super critical. The important point, though, is that this does account for the anti-stereoselectivity of the reaction, with the trans 1,2-dibromoalkene being the favored product here. The subsequent halogenation, if we use a second equivalent of X2, occurs just as we saw for halogenations of alkenes. This is an alkene, after all, so we would expect a halonium ion, SN2 opening by bromide of that halonium ion, so on and so forth, and the product we end up with here is a 1,1,2,2 tetrabromoalkane. Ozonolysis of alkynes is also possible, and here we end up not with ketones or aldehydes, but with carboxylic acids. All we need to do is treat the alkyne with O3 and H2O. There's no need for a reducing agent here. Water just hydrolyzes the intermediates after O3 reacts with the alkyne, adds to the alkyne, and we get potentially up to 2 carboxylic acids if the R1 and R2 groups are different. If R1 and R2 are the same, we end up with 2 equivalents of the same carboxylic acid product. Won't get into the mechanistic details here. We'll just say that this is a useful way to produce carboxylic acids from alkynes. One thing to note is if we use terminal alkynes or acetylene here, we end up not with formic acid, which would be the product if we imagined a similar thing happening to the above with a carboxyl group linked to H. We actually don't end up with this. Instead, we end up with carbon dioxide here, CO2, and the carboxylic acid corresponding to the other end of the terminal alkyne, or 2 equivalents of CO2 if we hit acetylene with O3 followed by water.